In the previous lecture, we placed Wess-Zumino quantum mechanics on the lattice, solved the fermion doubling problem using a Wilson term, and preserved one of its two supercharges. In this lecture, we extend that logic to BFSS3, which can be viewed as a lower dimensional approximation to M-matrix theory. Here, we will again deal with fermion doubling, but now in a gauge covariant setting, making sure that gauge symmetry is fully respected on the lattice. It's important to recall that gauge invariance and supersymmetry play very different roles. Gauge symmetry is a local freedom of our description. If we break it, we lose unitarity and charge conservation. Supersymmetry, by contrast, is a global spacetime symmetry. It can be broken softly by the lattice and still be recovered in the continuum limit as long as the discretization preserves enough structure to control quantum corrections. We thus turn now to the BFSS three-dimensional matrix model and its mass-deformed version, BMN3. This model is obtained by dimensional reduction of three-dimensional supersymmetric Yang-Mills theory down to 0 + 1 dimensions. In other words, it is a matrix quantum mechanics, a one-dimensional gauge theory with time as the only continuous variable. Physically, it serves as a lower dimensional approximation to the 10-dimensional BFSS or M-matrix theory, and to its mass-deformed extension, the BMN model. We work in the T-Hooft limit, where 1/g² equals n, and we adopt the Euclidean formulation with periodic boundary conditions, corresponding to finite temperature. The lattice gauge fixing of the bosonic sector follows the same procedure as in any BFSS model, regardless of dimension. The Euclidean BFSS3 action is given in equation 21. The fields XA psi and AT are all Hermitian n by n matrices in the adjoint representation of SU of n, and the covariant derivative acts as dt equals partial t minus I times the commutator with AT. The gamma matrices in 3 dimensions are given in equation 22. The charge conjugation matrix is C sub 3 equals minus sigma 2, and the Majorana condition reads psi bar equals psi dagger gamma 0, which is also psi transpose C sub 3. The Majorana spinor psi can thus be written as a two-component column vector with components psi 1, psi 2, with the constraint that psi 1 dagger equals psi 2 equals psi over square root of 2. These definitions ensure that the Euclidean action is real, and they carry over consistently to the lattice formulation. To analyze fermion doubling in the BFSS3 matrix model, we can safely restrict to the Gaussian regime, that is, the large mu limit with a sub t equals 0. In this approximation, the action reduces to the form shown in equation 24. This structure is almost identical to that of Wess-Zumino quantum mechanics, a real bosonic coordinate, a complex fermion, and a quadratic superpotential term. As a result, the same doubling problem arises here. The naive antisymmetric lattice derivative produces two light fermionic branches, one physical and one spurious, at p equals 0 and p equals pi. Therefore, the strategy to fix it will be the same. Introduce a Wilson term to lift the doubler while preserving the correct low-energy dynamics. On the lattice, the Gaussian action becomes a double sum over sites n and m with two kinetic operators, k sub nm acting on the bosonic matrices xy and d sub nm acting on the fermions psi. The discretized Gaussian action is given in equation 25. In the naive central difference scheme, the derivative partial t is replaced by the antisymmetric lattice derivative partial a. This gives k sub nm equals minus partial a squared sub nm plus mu squared over 36 times delta nm, and d sub nm equals partial a sub nm plus mu over 4 times delta nm. But this naive discretization immediately recreates the fermion doubler, since the antisymmetric derivative produces two linear branches in its spectrum, one at p equals 0 and one at p equals pi. To eliminate this extra light mode, we introduce the Wilson deformation, adding a Laplacian correction, as shown in equation 27. This Wilson prescription lifts the doubler by giving it a heavy mass of order 1 over a, while keeping the physical small momentum branch light and unchanged in the continuum limit. In other words, we have now achieved on the lattice what we learned from the Wess-Zumino model. Fermion doubling is removed, and the fermionic kinetic term of the BFSS3 model takes a consistent, continuum-safe form. After introducing the Wilson correction, we can rewrite both the bosonic and fermionic lattice operators in a more symmetric form in equations 28 and 29. To maintain consistency between the bosonic and fermionic sectors, we introduce a small correction to the bosonic kernel given by the action delta S in equation 30, with delta K sub nm equals a squared times rb squared minus rb prime squared times the Laplacian delta squared over 4. This fine-tuning disentangles the bosonic and fermionic Wilson parameters, allowing each sector to be adjusted independently. The final no-doubling prescription is then given in equation 31. With this form, both sectors share the same lattice Laplacian structure, and the fermion doubler is completely lifted while the continuum limit remains intact. With the Wilson framework established, we now specialize to the no-doubling prescription corresponding to r equals 1. In this case, the lattice fermionic part of the Gaussian BFSS3 action is given, in terms of the backward and forward derivatives, by the first or second lines in equation 32. Symmetrizing these two equivalent expressions, this free fermion action takes the compact, manifestly antisymmetric form given in equation 33. The corresponding free massless Dirac operator is a 2x2 matrix with zeros on the diagonal and off-diagonal entries, partial L and partial R, which the backward and forward derivatives respectively. This removes fermion doubling completely while preserving the correct continuum limit and maintaining the physical structure of the BFSS fermionic sector. We now introduce gauge coupling by replacing finite differences with covariant differences. The forward and backward covariant derivatives become script d plus and script d minus, which are defined in terms of the link variables u sub n plus 1 and u sub n minus 1n in equations 35 and 36. We then gauge fix to a uniform holonomy. Concretely, set every link u sub nn plus 1 to the same constant matrix d lambda. With this choice, the covariant derivatives script d plus and script d minus become given by the expressions shown in equation 37. An equivalent last link gauge fixing can also be used, in which we place the entire holonomy on the final link. We now arrive at the gauge fixed lattice Dirac operator, the central object of this construction. The fermionic part of the gauge fixed Gaussian BFSS3 action, in its no doubling form, is then given in equation 38. The gauge-fixed free massless Dirac operator, denoted by script d, is written explicitly in equation 39. It is a 2x2 matrix with zeros on the diagonal and off-diagonal entries script d minus and script d plus. Script d is antisymmetric, meaning its transpose equals minus itself. This property ensures that the lattice gauge-fixed free Dirac fermion action is real and that the Pfaffian, its determinant's square root, is well defined. The replacement, shown in equation 40, is the core result of this lecture. The continuum-free Dirac operator IC 3 gamma E0 dt goes on the lattice to the matrix script D. This prescription removes fermion doubling and maintains the correct continuum limit. We now include Wilson terms for a general R. Replace partial A by partial A minus RA over 2 times delta. The Dirac-Wilson blocks are modified as follows. Script d plus becomes script d plus r sub f times a times delta over 2, and d minus becomes d minus minus r sub f times a times delta over 2, as shown in equation 44. Recall that r sub f is r minus 1. Including the bosonic Wilson terms, the kinetic operator is modified to delta plus rb squared a squared over 4 times delta squared, as shown in equation 45, provided the bosonic and fermionic Wilson parameters satisfy the relation given in equation 46. Finally, we make the Wilson terms gauge covariant. Wherever script d plus and script d minus appear, we replace them by their gauge covariant versions, using link variables as before. The only new ingredient is the gauge covariant Laplacian, required in both the fermionic and bosonic Wilson terms, and defined in equation 47. This ensures that both fermionic and bosonic Wilson terms remain fully gauge covariant and consistent with the fixed holonomy background. Here is the final lattice prescription. The continuum-free Dirac operator IC3 gamma E0 dt is replaced on the lattice by the Dirac-Wilson matrix, a 2x2 operator with zeros on the diagonal an off-diagonal block script d minus minus RFA over 2 delta, and script d plus plus RFA over 2 delta. Script d plus and script d minus are the gauge covariant forward and backward differences, and delta is the gauge covariant Laplacian, equal to d minus times d plus. The parameter Rf controls the Wilson lifting of the doubler, giving it a gap of order 1 over a, while the physical small momentum branch stays light. The operator is real and antisymmetric, so the continuum limit is recovered. The Majorana sector, which includes both the mass term and the commutator coupling with the bosons, is carried over to the lattice trivially because it is a local interaction and does not depend on derivatives.